continue on Chapter-16. We're going to study the reactivity of ethers. So we just studied Chapter-16 how to prepare ethers. And the reactivity of ethers is relatively simple. We know ether can be oxidized, even though this reaction is not very useful. But sometimes in the lab you have to be careful if you have ether like those bottles are open to the air, even briefly. Then if you close the bottle and let the ether stay there for a couple of days, and then the ether will change into peroxide. And the ether peroxide is very explosive, and it has a hazard. So the reaction you can see in this chapter is important, kind of useful, is the acid-catalyzed cleavage of ethers. It's very similar as the carbon-oxygen bond of alcohol. We know alcohol can be changed into the air-pure halide. So therefore, the ether, you can do the similar reaction to the ethers. And you have this R prime, the general reactions. What is like interesting is when you have the ether, you can also actually produce two air-pure halide. So the general reaction on the top will give you one air-pure halide, one alcohol. We know alcohol can also react with HBr and HCl and produce those another air-pure halide. So at the end, you will see you will have two air-pure halide, Rx and R'(X). Okay, one example of this is you take this ether and react with HBr, and you produce two air-pure halide. One is this 2-bromobutane, the other one is methyl bromide or bromomethane. Okay, I think you still like the diagnose with blind. So let me just change that into the blind so I can try something on this. Okay, so the reaction of ethers, one reaction of ether is with those hydrogen halides, HBr, HCl, and this pretty much cleavage the carbon-oxygen bond. Okay, here is the reaction, the examples. The examples, we have this sec-butyl methyl ether, and you can do a bond breaking, the bond between carbon and oxygen. So both of the bond between carbon and oxygen will break. So you will produce, as if we add in HBr, and then you add in your heat. So when you produce two air-pure halide. So both of the carbon-oxygen bond, initially there's oxygen here, so then this bond breaks, and you produce this. This becomes the Br. And then the other oxygen carbon bond also break, and you produce the BrCH3. The other product, the other side product is H2O. You want to write 16.9 is we have a series of di-alkyl ethers that was allowed to react with excess hydrogen bromide with the following result. Then identify ethers in each case. So the first question is one ether give a mixture of bromocyclopentane and one bromobutane. Okay, you have some of the ethers, so with some of those excess HBr, then heat. What that ether produce is bromocyclopentane, and bromo. Okay. Also plus one bromobutane. So this will be our one bromobutane. So then you want to reconstruct your ether. When you see the last example, when you have the ether reacting with HBr with heat, both the carbon O bond break. So this ether actually is this cyclopentanol and butyl cyclopentanol ether. So you have this ether here. So sometimes I will give you the product and ask you what will be the reagent. And then you will see what reagent produces the product. And the second pattern is another ether give only benzyl bromide. Okay? So that means give you two benzyl bromide. Benzyl bromide, that's it, benzyl bromide. So you have benzene, benzyl, this will be the benzyl carbon, bromide, so you're adding the Br here. And the similar, so what reagent produces? So you produce two of these. You will use excess HBr, then heat. Let's say you take two of those HBr. And then what will be the ether? So you need this type of ether to produce the benzyl bromide. Okay? Because you produce both, you only produce the benzyl bromide. Usually you will produce two of those alkyl halide. But this time, that means we have this dibenzyl ether. Okay, now pattern C. The ether give one mole of 1,5-dibromopentane per mole of ether. You get like a dibromopentane. So in one molecular you have okay. Let's see that the product. Dibromo, so a Br here, and Br here, and say that 1,5-dibromo. This is 1,5-dibromo. So it comes from the resin of the ethers with let's say 2 HBr. So ether has 5 carbons, and then ether has oxygen, and then oxygen will bond into 2 carbons. So what you see, if you have 5 carbon and then one oxygen, because you only produce one of this. So one more ether produces one more of this. So that gives you some idea your ether is a cyclic ether. Right? The cyclic ether has 5 carbon, 1 O, that means you have a 6-member ring. It looks like a benzene. Okay? But one of the carbon.
What page are you on?
Huh?
What page are you on?
What the page, let's see the page number 16 on the
16.
yeah. Get on to that section is the reactivity of ether. Okay? And this is the problem, looking for the problem 16.9. We're looking for the problem 16.9. I think, okay. Now, what is the mechanism? Usually the mechanism will help you to memorize the equation that makes sense, those reactions. Let's use the example of the diethyl ether with HBr, produce 2 of those ether bromide plus water. Diethyl ether, you know the sulfur, so we have ether, and then 1 oxygen, and we have another ether, diethyl ether. So this will take those, as usually take 2 HBr as what we write before, those examples, with heat. It produces 2 of this ether bromide, then plus H2O. We want to see what is the reaction mechanism for this reaction. And I said I will usually give you the step, I give the name. So the step 1 is the proton transfer to the oxygen of the ether to give a dialkyl of sodium ion. So what that means, you will take this diethyl ether, and you also have another reactant which is HBr. Now you can draw the 3 lone pair of Br, and you can also draw out the 2 lone pair of oxygen. So the protonation, the proton transfer of oxygen, proton transfer to the oxygen of the ether, that means you will take the 2 electrons from the oxygen and grab that and like this. So this reaction is kind of a faster reaction. And you produce this, and this is sort of the dialkyl of the sodium ion. And in the same time, you produce the Br1 negative. And the second step, your nucleophilic attack on this intermediate. So let's take our nucleophile Br1 negative, and let's take our intermediate, which has a 1 lone pair electron and have this positive charge. This will be the S-N2 reaction. You have this 2 ether symmetrical. I mean, there's 2 alkyl here. Here the ether has ether. If not symmetrical, if here is isopropyl, here is methyl, which one is going to attack? So we will not study those. So right now we just say this was the same. We can take this bromide and attack either one of these. And then this will, push these two electrons on this positive charge, oxygen. And this will be a slow step. What you first produce is this Br will add on that side, and in the same time you produce this alcohol. O and H and that. And we said in our general or the overall reaction, we produce two acyl bromide. Okay? Now we have one acyl bromide and one acyl alcohol. And then you know what happened if we remember what we did for chapter 15. You have alcohol and you have a lot of those HBr. So the HBr reacting with that alcohol. So I will take that alcohol and I will rearrange the structure like that, and then you have the HBr, and it's a very quick step. And you first will also do the protonation of your oxygen. So you will take this carbon electron and transfer here, and like this. So this step is the fastest step. So you produce, initially you have one H, now you're adding on one more H. Now this oxygen has a 3 bonds, so therefore it becomes a positive charge. And then plus Br, the bromide. Right? And this Br bromide is produced still in the vicinity of this molecule can go on to the next step to the SN2 reaction. Okay? So the SN2 reaction will happen like this. And I will say this will produce our other acyl bromide. Here also plus H2O. So this is the mechanism. For this example, you have a diacyl ether. So this acyl is sort of alkyl group, not the aryl. If aryl, like in bending, and you probably will not finish the last step, step 3. If my acyl, like not acyl become like the phenol, like this, and you add in HBr and heat. What you will produce is phenol, which is a kind of alcohol. We'll start in chapter 21, and then plus this guy. So a little different than we have this dialkyl ethers. We have alkyl and aryl ethers, and you break one of those bonds, oxygen and carbon bond, and you don't break the oxygen and carbon bond out to the aryl part. So with each of the type of R or R prime, R not the same as R prime, which means the unsymmetrical ethers. The question is which of the carbon oxygen bond to break first. It's not the one that we need to use them in this level of study. Also notice the tertiary alcohol reaction with hydrogen halide by the SN1 reactions, which means in step 3 in the mechanism, if you produce a tertiary alcohol, you don't have to see this S and 2 reaction as I showed here. You can see those S and 1. So this is about the first part of the Chapter-16. Chapter-16, the next part is more reactions, is about the epoxide. Epoxide is a very important intermediate compound in organic chemistry. You can see you can use it to produce alcohols. Alcohol is very important because you can change alcohol into many other functional groups. So we are going to study two main methods to prepare the epoxide. The first is the epoxidation of alkene with peroxide acid. Second method is the base promoted ring closure of vinyl halohydrins. Let's examine these two in details. So the first one is the so-called epoxidation of alkene with peroxide acid. So this general reaction I give to you, I do not give you the reactions. By the name, that means you want to produce this epoxide, and you want to use peroxide acid. You can use MCPDA, or you can use some other peroxide acid. Let's write a general generic alkene. So we have R2C double bond and C and R2. So then you plus those peroxide acid. I think the peroxide acid I'm going to use R prime and then C double bond to the O, and I have O and H. So this is so-called peroxide acid. Usually the carboxylic acid, so the usual acid, you will have the structure R or R prime, C, O, O, H. So briefly, the mechanism is kind of interesting. If I take a double bond like this, and I have a R and a C bond, and so let's see, I have O and H like that. Okay, so these are peroxide acid. And double bond have an electron, so the electron from double bond get onto the oxygen. Then these two electrons from that get onto the other carbon. And some electron from that oxygen grab this proton, and then this bounce into that. And you pretty much see all this is the structure. So what you produce is not this single double bond. You will produce a single bond here. And then this O is grab away from your peroxide acid. And then the other part of the peroxide acid, so we have that C. And that O become OH, and the other O become double bond O. So that's our acid. These two electrons here, this two electrons here, they come from this bond here, the double bond here. You don't have to worry about the mechanism like what I just showed you. If you're just sometimes just curious about how can the peroxide acid change the double bond into epoxide. And there's also a stereochemistry program. So you can see here, you have this, you produce this these ring structures, and I only show the structure basically like that. I did not show you the stereochemistry. So if we have this program, you don't have to worry about the stereochemistry, but just you know you can produce if you produce like those color centers, then your product can be the mirror image, or the methyl compound. So then the sharpless epoxidation, sharpless is the name of a scientist who was a professor at MIT. So he developed a very useful approach to synthetic some of those epoxides from the earlier or allylic alcohol. Allylic alcohol is this type, and then with some of those special catalysts. So the catalyst, the special is one catalyst use this titanium catalyst. In addition to that, it use one like those enantiomer of the tartarate. And this picture shows you the tartarate. And he used 2R, 3R, and he will produce a special. Epoxide like this. And this epoxide produced only like one enantiomer, 98%. That's very, very good high yield. So the other enantiomer is not in the product. If you don't use those special catalysts, and you will produce a racemic mixture, which means 50% work with 2S, 3S, the other 50% work with 2R, 3R. So if you want to review this kind of the so-called Ingold pre-log priority, and you can sign this two color center, and then you will be able to find out. So like the 2S and 3S is right. So we have a wedge, and then we have this carbon here. We have a dash. Then we have the OH. If you want to sign the priority, okay. Let's say for this carbon here, this is the color center, okay. And you have this. The highest priority is this oxygen number 1. Then you have this carbon here for the number 2. So this carbon here will be a number 3. So this 3 carbon and 1 oxygen. You have a H did not show on this carbon. So H is pointing out of the screen like towards you. Then you see this structure, so right now you go from 1 to 3 clockwise, and it looks like the R configuration, but because your lowest priority number 4 is pointing to you, so you don't use that rule, you just opposite. So this means this right here is sort of the S configuration. And use the similar approach, you will find out. So this carbon here is also the S configuration. right? Now let's see if that's right. So let me erase those. I will reassign our priorities for the carbon on the right side. Priority again, so this is the substituent on the for the right carbon. So oxygen has the largest atomic number. Compared with carbon is larger. So this is number 1. And then this will be number 2. Because that carbon bound to 1 oxygen. Okay. Now this carbon will be number 3. So in this is consider the configuration of this carbon. Right now this carbon only shows 3 chemical bonds. There's 1 chemical bond missing. So in those line structures, the bond that is missing is the bond bonding to the H. Okay. The bond bonding to the H, this is a wedge. So bonding to the H is a dash. So there are some of those dash to the H. Dash means the H is in the back of the spring. Is away from you. Or is away from you, then you have just use the usual rule. Okay? If there are 3 other group is clockwise, it will be R. If counterclockwise, it will be S. And in this picture, so your H is far away from you, the other 3 group is counterclockwise. So therefore it's S. And so that's the reason we have this called the 3S and 2S and 3S. So that's briefly a review about the configurations. I probably on the final exam will see those because the final exam is both orbital 1 and orbital 2. But for this particular reaction, when you see those epoxidation of those alkane with propionic acid, just show me you have the epoxide. So this is the first way of prepare the epoxide. The second way of prepare the epoxide is base promoted the ring closure of single halohydrins. Halohydrin you can produce from the reaction of the double bond with halogen and in water. Halohydrin, so this hydrogen, that's a halogen. Single. So the reaction is base promoted. So first, you will see the reaction with a base and produce the epoxide. Let's take a simple single halohydrins. Let's see, we have X. Sometimes you write your reaction in like this. So you will write hydroxide, and you will see probably a lot of time in those biochemistry. That means you have a hydroxide as reactant and turn into water as a product. And you can, if you want to change the way you write, you will see plus. OH1 negative here, then you can use water here. So I can use those arrows, that means, so this is one of the reactant and the product. So what happens is you're doing something like this. You will take this, so if you want to use electron flow arrows, you take this and this. Next step, you have this is a very good nucleophile, this epoxide. Now here is the halogens. So halogen is the electron withdrawal. So because this carbon positive charge of the carbon and attract to some of those electrophiles and become a good electrophile. So and plus the halide. Okay, any questions or comments? Yeah, so the last step is the intermolecular SN2 reaction. And the SN2 reaction, that means your nucleophile attack your carbon from the back side. And you can see from this example, if we have this single bromo hydrogen, and we have the OH is above this cyclohexene ring, and we have the H underneath. On the other side, we have a H that is above the ring, and we have the Br is underneath the ring. So if we take this molecular and we add in OH, sodium hydroxide, and you first use sodium hydroxide, take the H away from here, you produce alkoxide. So alkoxide will our nucleophile attack on this carbon from the top, and push the Br away, and at the same time push the H below this cyclohexene. See right now this H is on the top. So when this alkoxide attack this carbon, that will push that below this or behind this screen. In the same time, this Br will add the even over here. So this is called the SN2 reaction. Okay? So if you see the structure, and the structure looks like this. So you will have this epoxide, and you still have the H below the ring. Now the Br is not here anymore. The Br is gone. Okay? And so then this H, so that H was on the top is also be like behind. With the so-called trans-diaxial arrangement of oxygen and halide. If you want to see those chair structures for cyclohexene, and you will have the chair conformation of your cyclohexene. Okay. And let's see, we will draw those all those H out. And here you have Br, and here H, and here you have your OH. So this diaxial OH with Br. Remember in the cyclohexene, you have the chair conformation, and some of those bond is axial, and some other bond is equatorial. So this H, this 2H here is equatorial. This Br and OH is axial. Axial, that means it goes straight up and down, perpendicular, kind of perpendicular to a ring. A ring is not like very flat. I said before, I don't want you to draw like the enantiomers for the product of the epoxide, but you need to draw those cis and trans isomers. Okay? That means if you start with if you start with cis-butane, okay, as you start with cis-butane and cis-2-pentene like this, so you have a H and you have H. And if you add in the OH and Br, and OH and Br is adding anti from the opposite side. Anti addition first, OH and Br. Anti addition. What you produce is this structure, so the Br, let's see, on the top. And the H here getting a little lower, and the metal getting a little lower. The OH get on from the other side. OH getting from the other side. And you still have the metal, you still have this H here. Now, when you so this step you produce the what's your halohydrogen. The next step is base-catalyzed ring closure. Okay? Which means you use some of the base, you will take this H away, then become alkoxide. The alkoxide become very good nucleophile attack the carbon from underneath and push that Br out. And what you can see will produce, so that's it. This was the inversion of configuration. And obviously we use some of those bases. Epoxide ring here, so this is where we are O. And like this. To emphasize this bond in the front, they use like a wedge. So what I said is you don't have to say you will have another enantiomer. Okay? You don't have to worry about that. You just have to show if you start with your cis double bond, cis like 2-butane, okay? And you want to show like the epoxide you produce also have these two metal on the same side. Okay? Now this picture show you here. If you have this epoxide ring, is like cutting into the spring, and you have the two metal on the left side, and you have that 2H on the right side. So you keep that cis configuration for your two metals. Right? So now if you have the trans, okay, if we start with trans, we still have double bond. Now the trans, let's see, I will put this metal here, and then this is here. Then I have the metal on the other side. Okay. Similar process, two-step. First, you will see this anti-addition. The anti-addition of this time, you produce the lead H, and this is still a Br, and your hydrogen. base. With some base. The base will take the H away from this hydroxyl and change the hydroxyl into epoxide ion, very good nucleophile. Then your ring will get a ring from the underneath this structure. We see like the result. The result. So this will be H in vessel and under vessel. Let me keep the initial configuration. I will measure on the other side. So this is measure. And here is H. And here is our. If I draw the other way, over the enantiomers. And here is O. And here is the other bond. And that's O. Right. So now this time let me again emphasize this ring is really cutting into the edge like that. Any questions? So this section, the second part of this chapter is about the epoxide. Right? How many ways to prepare the epoxide? 2 ways. What is the first way to prepare the epoxide? Use styrofoam. I think 2 ways, both of the ways use dust. You can think about starting styrofoam. The first way start with styrofoam and then what do you use? For oxalic acid. And the second way is you also start with double bond, and then you change the double bond into the Wacinial halohydrin, like what we just saw, right? So this is Wacinial adjacent, the halohydrin. Then we use the base and have the ring closure. So once we prepare the epoxide, and then we will study the reactions of epoxide. So the reaction, one is the reaction with anionic nucleophiles, which means you have some of those nucleophiles, and under the basic condition. Under the basic condition, so you will keep those anion nucleophiles. Otherwise, most of the nucleophile is basic, so you will protonate your nucleophile, then you will not have a good nucleophile. So under these conditions, under basic condition or under acid condition, those nucleophile reacting with your epoxide will open the ring because the ring has a lot of angle strength. So one generic equation, you will take this epoxide, very simple epoxide, add the oxide, you add in a Grignard. Grignard, even though you do not see the anion, right? But in the Grignard, the magnesium is plus charged cation, and R is kind of a relatively negatively charged anion. And the result is you add this R onto one carbon, and you break this bond, and you still have the bond between the other carbon O, and then you protonate with the warm up, you produce alcohol. So you produce alcohol with Grignard, you have 2 more carbon. Right? And you produce a primary alcohol. In last chapter, you studied if I take the Grignard, RMGX, I can add on 1 carbon and produce a primary alcohol by using what we studied in last chapter, chapter 15. I can produce R and C just adding one more C compared with R or C2, and then OH. What we use in last chapter is the formaldehyde. And to get this, and if you use green yarn, you have to use 2 steps. So your first step must be in those aprotic solvent. Then your second step, you use some of those acids to protonate what you produce. So you can see like how you sometimes you want to see like how much more carbon you want to add and produce a primary electrolyte relatively simple. If you take a green yarn like what we were doing in the lab, if you take a green yarn and reacting with carbon dioxide, CO2, you will produce a carboxylic acid with 1 more carbon compared with your R. So all those, when you do the synthetic approach, you can always think about you can produce an acid, then you can reduce acid into alcohols, or you can produce the alcohol directly by using the green yarn with formaldehyde or aldehyde. Right? So that's kind of like a review. But anyhow, if you do like for this chapter, you take epoxide and reacting with those anion nucleophiles, you will see you will open the epoxide. And more important, later on you will see your anion nucleophile will attack the epoxide from the less south T2 side if you are in the base conditions. So we talked about that before. But right now, you don't have the choice. Your epoxide is symmetrical. Okay? Now for this. Okay, so let's finish this one and we'll have a break. Okay? So this example, what about our nucleophile? Our nucleophile actually is this. So usually you write that together with some of those counter ions. Okay? So this is really the nucleophile. Okay? And so what you will produce, let me draw this part first. So this part comes from our initial epoxide. Then the other carbon will go into the S. So that is the result of the nucleophile attack. And then let's finish the final result. So I briefly look at the homework for the Chapter-16, and you will see a lot of those reactions. Okay? And you can see, even though there are many reactions, but the pattern are similar. If you identify your nucleophile is anion in basic condition, and if you have a choice, just choose that nucleophile if you, in basic condition attached to the carbon that has like a few less carbon in the epoxide. If on acidic condition, you just do the opposite. And we'll see a few examples of those nuclear fire attack open the epoxide ring from the side is like a little more crowded. So the base attack, you kind of make a usual sense because if there's crowded, you just there's a lot of those hindrance. Okay? And the acid conditions, the attack from the crowded side has the electronic reason. Okay? So we'll study that after the break. And so let's take like a 5 minutes break.
5 minutes, that's it?
We take a 5 minute break at one time, and then next time we'll do the group.
So are you going to start exam 2?
Probably use that. done? Curve hard is not curve, yes.